Welcome to this presentation on the Davis-Besse Reactor Pressure Vessel Head Degradation. My name is Raymond Spornhauer. I'm a member of Team Alpha, and this project is part of the Nuclear Engineering Technology Capstone for Thomas Edison State College. In this presentation, I will talk about why this event is important, then I'll cover a general synopsis followed by a detailed description of the event, then I'll talk about the lessons learned and close out with conclusions. Why this event is important. The reactor vessel head sits on top of the reactor vessel and is part of the primary pressure boundary, which is designed to withstand up to 2,500 pounds. Normal operating pressure is about 2,000 pounds. It also contains the penetrations for the control rod drive mechanisms and various other in-core instrumentation. It is made up of 6.63 inches of low alloy stainless steel on top of a 3/8 inch cladding of type 308 stainless steel. The boric acid had corroded the low alloy stainless steel around some CRDM nozzles all the way down to the cladding, which alone was not designed for these pressures. This could have resulted in an unisolable loss of coolant accident and initiated the emergency response systems. A sudden catastrophic failure could have prevented a control rod from inserting during a reactor shutdown or caused a positive reactivity addition. Debris from such a failure could have affected other safety components and backup systems. During a scheduled refueling outage in 2002, workers inspecting CRDM nozzles identified 5 CRDMs with through-wall leakage at the nozzles. While attempting to repair these nozzles, they found additional significant damage to the reactor vessel head. Davis-Besse at this time was considered by the NRC to be among the best performing plants in Region 3, with IMPO finding no significant weaknesses and improving performance trends. This resulted in less vigorous inspections and dismissal of some indicators because they believed the plant was safe. The following are a list of indicators of the boric acid corrosion at Davis-Besse. On April 25, 1998, a condition report revealed fist-sized clumps of boric acid with light dusting covering the surface area of the vessel head. On September 18, 1998, workers notified the NRC that 2 of 8 pressurizer spray valve nuts were found missing with buildup of boric acid on the valve. On July 30, 1999, a condition report documenting the results of lab analysis indicated iron oxide from corrosion deposits on radiation monitors inside containment. On April 6 of 2000, a condition report identified lava-like boric acid had been discovered on the reactor vessel head during CRDM inspections. On April 23, 2001, a condition report identified radiation monitor filters inside containment requiring filter replacement every 14 days. The filters used to last for months. On July 23, 2001, the radiation monitor filters were required to be replaced every 2 to 7 days. The next 2 slides show a list of communications and responses by the Nuclear Regulatory Commission. On March 17, 1988, the NRC issued a generic letter 88-05 to address reactor coolant system leaks below tech spec limits to ensure boric acid corrosion did not result in pressure boundary degradation. On April 1, 1997, the NRC issued a generic letter 97-01 to address degradation of control rod drive mechanism nozzles and other vessel closure head penetrations. On June 4, 1999, Davis-Besse was issued a notice of violation for 2 violations for boric acid damage. On August 3, 2001, the NRC issued a Bulletin 2001-01 requiring plants identified as susceptible to CRDM nozzle cracking to submit justification for continued operation past the end of the year. On September 28, 2001, the NRC contacted Davis-Besse to discuss the CRDM nozzle cracking. On October 3, 2001, the NRC staff identified Davis-Besse as not meeting the technical basis proving conditions adverse to quality were being managed. Then on November 16, 2001, the NRC orders Davis-Besse to shut down by December 31st to conduct inspections. On December 4, 2001, the NRC agrees to allow Davis-Besse to continue to operate until their next scheduled outage without performing the inspections required by the Bulletin 2001-01. Their basis for this decision was that current regulations were being met, the defense in depth philosophy was maintained, sufficient safety margins were maintained, only a small increase in the core damage frequency resulted, and the basis for risk measurement is monitored during performance. And here are some of the management responses. On July 1, 1999, Davis-Besse responded to the notices of violation for the pressurizer spray valve nuts and promised it was developing a revision to the boric acid control program. On October 11, 2001, Davis-Besse briefs the NRC stating that all CRDM penetrations were verified to be free from boron deposits during the previous 2 outages. Then on October 24, 2001, they came back and told the NRC that 24 CRDM penetrations were not examined during the outage in 2000. On November 8, 2001, they show the NRC select portions of photographs and videos taken during the 1998 and 2000 outages. On November 28, 2001, they commit to a number of measures to continue to operate until the next outage, which is February 16, 2002. Up to this point, I've discussed the indicators, the NRC communications, and the management responses. Now let's look at the series of events that took place during the outage. On February 16, 2002, Davis-Besse shuts down the reactor for a scheduled outage. On February 21st, workers discover large boron accumulations on the reactor vessel head. On February 26th, the workers report more boron than expected on top of the reactor vessel head. On February 27th, ultrasonic testing reveals axial flaws in the weld region of the number 3 control rod. By the completion of the ultrasonic testing, 5 CRDM nozzles were identified to have axial crack indications, with 3 exhibiting through-wall leakage. On March 7th, bottom-up ultrasonic testing revealed significant degradation of the reactor vessel head. In this slide, we can see photographs taken at 2 of the nozzles where boric acid had significantly corroded the low-alloy steel. After being notified of these discoveries, on March 12, 2002, the NRC notifies pressurized water reactor plants of the reactor vessel head degradations that were discovered at Davis-Besse. They also charter an augmented inspection team to determine the history of the reactor coolant system operational leakage, the history of the reactor vessel head material condition, the history of the reactor vessel head inspections, and characterization of all reactor vessel head corrosion damage. Then the following day, they issue a confirmatory letter requiring quarantine of all components associated with the damages, for Davis-Besse to initiate a root cause analysis and evaluate the extent of condition, and for the plant to obtain NRC approval for repair of the reactor vessel head and to restart the reactor. On March 18th, the NRC requires all pressurized water reactor owners to provide information about their reactor vessel head inspections. On April 4th, the NRC alerts all pressurized water reactor owners of warning signs overlooked at Davis-Besse. On April 29th, they invoke the manual Chapter 350 process to oversee restart activities at Davis-Besse. On May 15th, they issue a revision to their confirmatory action letter and charter a lessons learned task force. On August 16th, Davis-Besse has issued a restart checklist identifying restart issues. On September 30th, the Lessons Learned Task Force final report was issued identifying 51 recommendations to prevent a similar event from happening again. On October 30th, they notified Davis-Besse that containment sump modifications were required before startup. On February 25, 2003, the NRC issues Davis-Besse a red finding for damages to the reactor vessel head. Then October 7th, they issue yellow finding violations for high-pressure injection pump vulnerabilities all the way back from the date of commission. On March 8, 2004, the NRC closes the confirmatory action letter and approves restart of Davis-Besse. This slide is a list of management responses during the event. On March 22, 2002, Davis-Besse completed a preliminary probable cause analysis. By April 18th, they completed their root cause analysis, and on May 21st, they submit their return to service plans. By May 23rd, they had purchased an unused reactor vessel head. On August 15th, they had completed a root cause analysis for evaluation of management failures. On September 5th, they committed to resolve the management failure issues. On May 5th, 2003, the management team identifies the high-pressure injection pumps as vulnerable to possible debris from reactor vessel head failure. Then on February 12, 2004, Davis-Besse reports completing the restart checklist and requests for restart. The following are the results of the root cause analysis. The CRDM nozzle 3 crack had developed between 1987 and 1993. The crack began leaking between 1994 and 1996. Efforts during the 1998 refueling outage neither identified the leak nor removed boric acid covering the nozzle. Significant corrosion at the nozzle occurred during 1999, evident by the iron oxide in the containment atmosphere. Efforts during the 2000 refueling outage neither identified the leaking nozzle nor removed boric acid in that region. Additional minor damage was found at nozzle 2. The additional management issues identified in the root cause analysis include: the risk to the reactor plant vessel head surface was not recognized due to incorrect perceptions about the leakage and corrosion mechanisms of boric acid. Modifications were delayed to when they thought they would be more susceptible. There was insufficient management involvement in containment and at the reactor vessel head during the outage to assess the conditions. Many of the indicators of the boric acid corrosion were not recognized. System health reports indicated inconsistent conclusions between indications. The procedures for prior head inspections were not used. The reactor plant vessel head cleanings were not done correctly, nor specifications given. No standard restart structure was used to identify boric acid left on the head. The following are additional NRC inspection reports later identified as indicators to this event. On June 4, 1999, an inspection addressed the complete boric acid corrosion of 2 pressurizer spray valve nuts. July 20, 1999 described higher than normal reactor coolant system leakage. An August 20, 1999 report discussed reactor coolant system leakage that was causing containment radiation monitor filters to become clogged, along with the analysis showing iron oxide, a corrosion byproduct on the filters. October 8, 1999 discussed reactor coolant system leakage that was causing containment radiation monitor filters to become clogged, requiring replacement every 24 to 48 hours. There were 38 entries by the NRC resident inspector about boric acid deposits, accumulation, and effects on components that were discussed on daily phone calls. This slide shows a graph of the steady increase in unidentified reactor coolant system leakage from June of 2000 up to February of 2002. Here are some additional factors that were identified during this event. On June 24, 2004, workers initiated a condition report to inquire about the effects of boric acid on trisodium phosphate to control pH level in the event of a loss of coolant accident. On July 15th, workers inquired regarding the ability of backup safety systems to function properly if stainless steel from the damaged reactor vessel head created debris that could clog containment sumps. On May 5, 2003, management identified the high-pressure injection pumps were vulnerable to this debris. During the 2002 refueling outage, 15 5-gallon buckets of boric acid were removed from the containment air cooler's ductwork in plenum, and containment air sampling systems have been experiencing problems since 1999. Here is a list of other major upgrades that took place as a result of this event. Now we'll talk about some of the lessons learned by the NRC. The NRC worked with the American Society of Mechanical Engineers to develop long-term inspection requirements of reactor vessel heads and ordered all licensed plants to visually inspect the reactor vessel head surface areas for indications of leakage as well as using methods to detect cracks before leakage starts. The Reactor Operating Experience Program was established to collect and communicate industry events and lessons learned. A new webpage was created with an organization to evaluate and screen incoming reports. A new communication tool was established to notify NRC staff of developing OE in their areas of expertise. It was identified that federal regulations authorize the NRC to initiate enforcement actions whenever it lacks reasonable assurance that the licensee can operate safely. Several changes were made to enhance the NRC's ability to detect declining plant performance, including specific issues identified by this event. Deteriorating conditions that planned inspections, maintenance, and modification activities could have prevented and enabled earlier discovery were frequently deferred. They would increase evaluation of programs and actions related to long-standing unresolved problems. This includes 3-year audits of management programs. The NRC Inspector Training Program was enhanced by web-based systems. The reactor oversight process was strengthened to detect weaknesses in safety culture. There would be devoted resources to plants in extended outages or that have performance issues. And finally, they established a site staffing metric for permanent resident and senior resident staffing criteria for maintaining 90% coverage. Some of the lessons learned at Davis-Besse include improvements in their boric acid corrosion control program, the reactor coolant system integrated leakage program, their in-service inspection programs, and the addition of a leak monitoring system to enhance leak detection capabilities. Some of the lessons learned by the industry include EPRI's Material Reliability Program revised their safety assessment reports to become top-level documents for industry safety assessments. Westinghouse appointed a task team to develop generic guidance for an effective boric acid inspection program for pressurized water reactors to help meet the ASME requirements. INPO developed guidance for performing INPO review visits, pressurized water reactor primary system integrity, in order to promote excellent performance in boric acid corrosion control programs. Nuclear plants have established their own boric acid corrosion control programs with dedicated engineering teams and program owners. They also conduct frequent internal and external safety culture evaluations and general work environment surveys. In conclusion, the boric acid corrosion that took place on the Davis-Besse reactor vessel head is probably the worst known accident to not happen in the nuclear industry. While the potential significance of this event could have been catastrophic, the damages were caught before any serious plant damages took place. There were several indicators as to the degradation that was taking place with the reactor vessel head which could have been observed and actions taken to prevent this incident from happening in the first place. But it has revealed other important factors in the safe operation of nuclear power plants as well. Performance indicators and trends must be highly analyzed and critiqued by generation groups and their respective oversight groups. They must always be rigorous in their evaluations and strive for continuous improvement by maintaining a healthy questioning attitude and performing industry benchmarking. Management decision-making and involvement with plant evolutions and decisions is vital, along with maintaining a safety culture that supports raising concerns. Lessons learned and operating experience do not have to be limited to only be internal to your organization. The benefits of lessons learned from this incident have extended into many fields, including colleges, NASA, the military, and other companies. Thank you for watching. I hope this presentation has been informative, and if you have any questions, feel free to contact me through the information provided in the comments section below.